Sound test, sound test. We're a little bit late, but I think we will start 12:05. Okay, so live on Twitch. And live on YouTube. Good. No. Seems I won't be able today to highlight messages from YouTube. Error occurred. So annoying. Well, that's life. Okay, do I have the folder? Now we are doing dynamic programming. There is the template. Where is it? Here we go. Struggling with counting DP. Well, DP is a strange category. A lot of people struggle with it. I will only do iterative DP. In competitive programming, you should do iterative DP if you want to get good, let's say. And no, I will not do things recursively today. Also, I will not solve all the problems from DP today. I think it's reasonable to do maybe a third of those. Almost all of this I know, so it's not that I will struggle with it. But if I am to explain anything, then it takes time. The stream will be 2 hours. And I think in introductory problems, I split them into half. So like I did 12 one stream and 12 the other stream, but that second stream went over 3 hours. So maybe now what we'll do is around 40% of the problems today. 3, 5, 10, 15, 23. Yeah, I think if I do 10 problems today, they are roughly of increasing difficulty. If 10 today, then that will be a nice split into 3 parts. So let's say that this is our goal. Tips for iterative thinking and coding DP. Well, I will solve problems and I will explain as I go. I don't have a separate set of tips other than solving problems, and while solving I will explain stuff. Should I do anything else? If the chat becomes very active and then if I think that it's too distracting that we have chat above my head there, then I will hide it. Still, what I can do is, you know, show messages like this. View always on top. Okay. I think we are ready to start, or I'm ready to start. Dice combinations. And all the codes will later be in the GitHub repository, plus the links, custom links. So now in Twitch you will be able to use exclamation mark link. On YouTube, I guess I will paste. On Twitch, did you get it? Yeah. I think it's all set up. Great, then let's go. Dice combination. Oh yeah, I was supposed to advertise stuff. In Codeforces 2 weeks ago or a week ago, I announced my group classes. They start from €50 per month. You might be interested. It's general Codeforces problem solving. I choose nice problems and we discuss them next week. If you want to practice a lot, I think it's very beneficial to join. Now, dice combinations. Count the number of ways to construct the sum n by throwing a dice one or more times. Each throw produces an outcome between 1 and 6. For example, if n is 3, you have such ways. So always one by one you add one of the numbers from 1 to 6, and you want to get the sum of n. All basic DP problems should be solved like this, or most of them. We go from left to right through a sequence, or here it's a sequence of things we add. And one by one we made a decision, we consider possibilities of what happens, and always from the stuff that happened so far we keep information that is relevant to us, so we would know what is the next possible step, or we would know when to finish, or what is the answer. The relevant stuff we keep. In this problem, the only thing that we need to keep, the only relevant or important thing, is the sum of values, because at the end we want it to be n. For example, here, the sum of those values is 11, and nothing else matters. I don't need to keep any extra information. If I simulated this process with some kind of exponential solution that tries all possibilities, always I would just keep the the total sum of values so far. And that will be our dimension of the DP, or the array. Eventually it needs to go up to n. I will not today explain modulo operations, but I have a video on that on YouTube. If you search for my channel and modulo operations, you will understand what's going on with this. Now I want to say that dp of s is number of ways, because this is what we count, number of ways, to get sum s. At the end, as the answer, I will output dp of n. And initially, I start with the sum equal to 0. If I minimized or maximized the cost, sometimes here I would put 0 or infinity, plus infinity, something like this. But if it's number of ways, then I have one way to get 0. This is how I start. There is one way to start. And then for every sum that I have, I will fill this in a moment, there are 6 possible transitions, where I need to say dp of s plus I, because that's the new state, this is the new sum, plus equal the number of ways that I have here. If I had 10 ways to collect the sum s, or to create sum s, after each of those ways I can add the plus I, and I will have the way to get the sum s plus I. Because of modulo operations, I need to do it like this. And I don't want to get out of bounds errors, So either when creating the DP array, it needs to be slightly bigger than necessary, like this, or better, make it the proper size, so from 1 to n, or from 0 to n, but here you cannot transition to element that doesn't exist. So I will, for example, here add an if s plus I smaller or equal n. Otherwise, you are not allowed to transition. Finally, the s. The sum from which we will transition goes up to n minus 1, so this is correct. That being said, if you went smaller equal, that would also work, because then those transitions do nothing. Those are the states from which you transition. In particular, you start from 0. At the end, you have sum equal n minus 1, and from that, you can still transition to the sum n. Also, is the loudness okay? The voice today is okay? Let's see. For input 3, the output is 4. For input 100, the output is something. Okay, submit. I'm not sure what file it will display, so one moment. Okay. Submit. The codes will later be in the GitHub repository. That's also the case for the introductory problems chapter that I did last time. Okay, dice combination is done. Minimizing coins. Here's the link. Here's the link. Will I do hard problems category? Not in the next few weeks, maybe eventually. So far I did introductory problems, and now I'm doing DP. I'm aware of additional and advanced problems, but I don't have plans for them this month, for example. Can GPT-5 solve this? You can check. That being said, it's a public problem for which very likely ChatGPT trained already. So I would be surprised if it couldn't. It's not a complicated problem. Okay. Next task, minimizing coins. Each coin has positive integer value. Create sum of money x using the available coins, with the number of coins being minimal. For example, if you have coins with values 157 and you need to create 11, then you can use it. You can do 3 coins. So this time we minimize, and we want to get some sum. So it will be similar to last time, but this time dp of s needs to be mean number of coins used to get sum s. What do we read? We read n and x and the coin values. Let's number the coins from 0 to n minus 1. That's the input. At the end, I want to output C of, I want to get the sum of x. That's the output. I start from the sum 0, and this time I shouldn't put this, because this is supposed to be the number of coins, not the number of ways. The number of coins needed to get sum 0 is 0 coins. With empty set of coins, I can achieve that. But for everything else, for everything from 1 up to x, initially I need to set its number of coins needed not to 0, because then our answer at the end will be 0. I will not minimize it with anything else. Is there DP category hard problems, Nicholas? Instead, we will set it to infinity to say that this is impossible state. That's also what you would do in some graph problems like BFS or Dijkstra. When you minimize something, by default you set its value to infinity. So make this of that size, filled with infinity, and infinity equal to, I don't know, 1,000,000,005 should be enough. This is by default the value that I use. This is the only possible state. And now for every sum, I will transition from here. So this is already computed. Also, when I already compute this, already know the value of this, and now I do transitions to iterate what will be the next thing I use, I always call this push dp. Push dp. We know value of dp of s, and we propagate further to new values. The alternative to that is pull dp, which we will see today in some other problems. Can we fill each element with its value? We can, but it's not needed. In DP problems, again, usually you think about creating a sequence or moving for a sequence from left to right, and there is, if not needed, there is no point in getting ahead and unnecessarily filling some other states or values. I start from value 0 and I can add coins. I can say that coin with the sum 7 I can get with 1 coin, but it's not necessary if I just say that 0 sum I can get with 0 coins, and from every state, including 0, I will propagate. So what I'm doing is simpler than this, than what you're suggesting. That being said, what you're suggesting, if I here said, sorry, this was supposed to be dp, not c. If I here said dp of ci is equal 1, correct, but unnecessary. And generally, you don't want unnecessary stuff, because when you get to harder problems, you will just have extra, let's say, 20 lines of code instead of extra 1 line of code. Okay, now for every coin I consider using it, for every, let's say, coin among coins, if s plus coin doesn't exceed, not n, that's x. I don't like the fact that in 2 consecutive problems they use different variable names. The target sum is x. If this, then previously what we did is something like that. This time is different. This time we need to use minimum. So to this state, I minimize it with my state plus 1 new coin. What this means is, for example, if I know that the current sum s I can achieve using 20 coins, and now I consider 1 new coin, then in total I have 21 coins. And these 21 coins I put as a possible value of the dp here. So maybe if the sum equal 100 I can achieve with 20 coins, there is a coin with value 7, then what I'm saying is for sum 107, possible dp value is 21. That's the meaning. But this is not simply assignment of this becomes 21. Did I say 21? Yes. Instead, it's minimization. So whatever this value was before, it's still possible optimal value, but we minimize it 21. Again, same thing you would do in BFS or in Dijkstra. And DP, well, those are also kind of DP, just on a graph. Finally, they are telling us that we need to output -1 if sum is impossible. I will show you what happens if I don't do it. First, copy the input. The output is 3, that's correct. I will put a new line, which is not necessary, but it's easier to run in terminal and see the output. The output is 3 is correct. Now, if I instead modify this input, and I say that this is a coin, let's say 3, and I want to achieve the sum of 4, this is impossible. You cannot obtain sum 4 with those coins. What will happen if I run this is that the program prints infinity. That's the default value, the unachievable value. What I need to do here is if dp of x is equal infinity, or sometimes I just do this when it's greater than infinity, because maybe something else even propagated to it. Equality would be fine, but this is more general. It works for other problems too. So if this is infinity, then output -1 as the statement requested. I will here just replace it with -1. And now if I run again, it says -1 for this case that I created where it's impossible. Let's submit. Shouldn't I change the stream title? What is the stream title? Oh, yes, thank you. Thank you. On Twitch it's not updated, indeed. Thank you, Solaris. Vitaly, sure, but do not spam in the chat. No point in posting something 5 times. Okay, accepted. We're moving on. Before I start, let me tell you this. Actually, I don't think that those DP problems that are in CSES are the best easy problems for beginners. If you want to start with easier problems, go to AdCoder DP contest and start solving from the frog problems. Those are slightly easier. So this is the link. And I think that the frog 1 and 2 are, and even vacation is simpler than those coin problems that might confuse you a little bit, because also they are so similar to each other. Plus counting problems are tricky. Sometimes you can overcount or not. Like in coin combinations 1 and 2, one of them I remember is actually hard to solve for beginners, and they are confused why those two different problems should have separate codes. Okay, coin combinations 1. We have n coins, each has positive value. Your task is to calculate the number of ways to produce the sum x. And if this, then we have such ways. This is, I think, the same as the first problem, just with those values instead of 1 to 6. Other than that, it's the same. Also, for the first time, I will mention the time complexity, and I will talk a little bit about the exact runtime. So about tricks regarding modulo operations. Yeah, coin combinations 2 will be harder. So I could maybe copy the code, but it's not too much anyway. We read the input. We create the DP of size x plus 1, where the final output will be under DP of x. We start by saying the sum 0, there is one way to start. We have the modulo operation. And now for every sum, again, push DP. For every sum, I will propagate from it to next states. For every coin among coins, if s plus coin doesn't exceed x, then DP of s plus coin, we add the number of ways. We need modulo operations. Now, if you do this, let's analyze the time complexity. We have nested for loops. X, which is 1 million, times we iterate coins, there are 100 of them. The time complexity of this code is x times n, which is 100 times million, and that's barely okay. I think I would get accepted with this code, but to make it faster, I will here avoid the modulo operation. So instead of that, I will say DP of s plus coin plus equal DP of s, and now if this exceeded modulo, then subtract. This seems more complicated, but because I know that I will exceed modulo only at most once, for example, if this is 1,000,000,007, then the result of adding two values that are below that will be at most 2 billion something. So at most once you need to subtract modulo. Again, if you're confused by that, you can watch my modulo operations video on YouTube. But this is faster. Though it's a little bit annoying and it's easy to make a mistake here. So from now on, I will use a function for that. To add two numbers. And in DP problems, or generally in modulo problems, you can have that function and copy paste it. Then here this becomes add self 1, 2. So first value plus equal that, and if it becomes too big, then apply modulo operation. Eight indeed. The problem authors usually try not to require stuff like that, but sometimes you have a solution that is not identical to the intended one, and this might help. You see already I have 0.67 seconds. That's dangerous. It's close to 1 second. Actually, CSES, it's a great problem set, but I don't like time limits. This is too tight, and in languages other than C++, you likely will not get accepted. How do you decide push versus pull? Whatever feels natural. Whatever I come up with first, this is what I do. And with experience, what comes natural or first is usually the easier option. If you prefer to do this pull way, which I will do in some problems, I'm sure today, that's perfectly fine. And it's not that the code is longer or slower or faster. It's just different. So I'm not here showing always two solutions because it's not that one is better than the other. It's a flavor or preference. Also, again, I should have done that at the beginning. On YouTube, a long time ago, I made a series of lectures on DP. Should I click this or this? Oh, yeah, here's a playlist. So this is DP lectures. It's from 6 years ago. Apparently, we roughly have now an anniversary because I see that one is from 6 years ago, the other from 5 years ago. So apparently I did that in August. Here's the link to YouTube as well. And I think I there maybe explained the terms. Today I'm not doing a lecture on DP, it's problem solving of DP tasks. Can you solve every DP question iteratively? More than you can do recursively, but not all of them. 95% of problems you can do iteratively. There are problems where the order is not known, and arguably Dijkstra is such a problem. Well, actually Dijkstra do iteratively, but sometimes you don't do a for loop. Example of a problem that is done recursively, not iteratively, unless you really just simulate recursion, is something where you have numbers from 1 to 10 to 18, but only some of them will be visited. For example, you start from a big number and you can divide it by 2 or by 3, and then you will jump over a lot of other values. So recursion is needed if only some states are visited and you cannot make a for loop. Bolzano theorem, what is that? I think that's an overkill of a description. I cannot highlight this, but Yavin on YouTube asks, isn't using a function slower than modulo operator? No, it's not. In this previous task, by the way, compiler might optimize such a function to make it inline. There is even a command where you can force it to do it so. But no, the modulo operation is just very heavy. Digit DP is easier recursively? I mean, maybe it is. I don't know. I do things iteratively. Okay. Next task. Should I maybe copy paste the previous? Well, let's still. Coin combinations too. Consider again n coins, each with positive value. We need to count number of distinct ordered ways, where this time, as the example shows, we only consider increasing sequences with ties. Actually, I would call this number of unordered ways. So if we pay 2 plus 2 plus 3 coins, that's the same as 2 plus 3 plus 2 coins. Those are same things. So we were supposed to count this only once, or just like they suggested, we will count only increasing sequences. Which means that in this task, we are doing the same as in the previous one, but we need to do things in order. Now, how can you guarantee that? There are two ways of looking at it. Two ways. One is that, like I said for the first problem, DP are often considering some sequence of items or operations. We are going from left to right, we're making some choices, and we keep information about things so far, information that is relevant, that is enough for us to make the next step and to know when to stop and what is the answer. In this case, not only the sum of values is important or relevant, but also I cannot here use a coin 2 if here I used a coin 3. It needs to be increasing. So what is relevant for me after making choices for this prefix is also the last coin used, the most recently used coin, so last coin. From this, you can have a DP of sum by last coin. That's a DP of size 10 to 6 power by 100, which is 100 million elements, so 400 megabytes. That is okay, but even if it fits in memory, it will be quite slow to allocate that much memory and to use it. So instead, I'm going to get rid of a dimension of this DP, which is just a technique that you should know how to do. Always, I can say that the last coin always moves forward, so I will hope that what I can do is from, let's say, coin number 7, I will always move to coin number 8. It's okay to skip some coin, but for that I can just say that the coin number 8 I don't use even once. From that you can get some inefficient, incorrect idea that for every coin we should iterate how many times we use it. Maybe it will lead to some x log x times 100 time complexity. That's still too slow, but no, that's not the point. We want to do easy transitions like in previous problems, where the transition is a single line, not an extra for loop. It should be called coin arrangements. Maybe. Not combinations, I guess. So what I'm going to do is go with a second solution, or a fast way to implement this first solution, and that is, there are 100 coins. I want to have only 1 million elements in memory. What I'm going to do is iterate coins, and for every coin I will apply it to every sum possibly. Let me show you what it means. I will, well, copy paste this code. This is from the previous task where we didn't care about the sequence being increasing. We have this, we start like that, sure, but now for every coin, and because of me doing it this way, it automatically considers coin in some order. Doesn't even need to be increasing, it will be the order how they appear here, so, which means that I will not overcount different orders. And inside I will say for every sum, if s plus coin smaller equal x, then I do the transition. Add with modulo dp of s plus coin dp of s. And let me make sure that this actually works, but I think that's enough, though it needs some extra explaining. Yeah, it works. Submit. The difference from the previous code is that I iterated coins first, not the sum. Look, this previous task, coin combinations 1, I iterated the sum, then the coins. Here, the coins, then the sum. It's not some random idea that I had. It was because the task said that we applying coins one by one. So what I'm doing is, first I consider, let's say, coin number 2. And what it does is, first I have this. There is one way to achieve the sum 0. But I also have one way to achieve the sum 2, one way to achieve the sum 4, and so on. This, for example, is equivalent to saying 2 plus 2 plus 2. So now the DP, after considering the first coin with value 2, the DP knows what is the number of ways to achieve every sum only with this coin. And what happens when I move on to the next coin? to the next coin, is that those will be extended. For example, because this is already 1, it will apply dp of 9 equals 1 as well. It will, or let's say, increases it by 1. 6 plus the next coin is 3 in our example. 6 plus 3 is 9. And this corresponds to 2 plus 2 plus 2 plus 3. Versus in the previous problem, what happened is that, let's say that temporarily dp of 6 is equal 1, and it corresponds to this. Then possibly I expand it into, I do this, because it corresponds to such a sum. But then from this sum 9, I again consider all the coins. In particular, I will consider the sum 11, and that corresponds to something like that. So the sum 11 here, which should not be counted separately here, because this should be counted only when we do the 4 times 2 plus a 3. And this should be counted when we first consider coin 2, then consider coin 3. One more explanation that I have for what happened. By the way, this is also called knapsack, this kind of problem where we take item multiple times. It's called knapsack, just with many occurrences. Now let me make a drawing. This is a drawing for coin combinations too. One more way to think about it is as two-dimensional table, and that was the first solution. I'm just using memory more efficiently thanks to what I'm doing, where if I consider, let's say, the sum equal to 0, 1, 2, 3, 4, 5, 6, 7, and so on, and then I have the coins with values like 2, 3, 5, and so on, the coins given to me in the input. Initially, there is a way for me to be here. There is one way. And when I consider this coin, I say that I can move here, or here, or here, and so on. And from now on, I can use the next coin. Let's say the transition that I'm doing is actually that I allow this to happen. So this is the cell that says the sum is 2 and the next coin to use is 3. But I also consider this transition, and so on. The sum can be 8, the sum can be 6. And now also I can do nothing. Then I'm using coin 3. From 0, I can use this here, but I also can use it there. I can use from 0, I can add 3 twice. So I will be here, or I will be here, and so on. I can also go to 9. From this place, I can do nothing. I can transition by 3, I can transition by 6, and so on. There are a lot of transitions. But I don't want to iterate for every coin how many times I use it, because that increases time complexity. Instead, I'm using all of this using just one array, one dimension. So now you can forget about this. There is just one dimension with the sum. And from 0, thanks to the first coin, the coin with value 2, we transition to 2. From that we transition to 4, and so on. When I say transition, it means we consider that this is the next coin that we use in the sum. And in the code, what we maintain is for every sum, how many ways there were to get here, how many possible paths, or how many ways to create a sequence of coins. So for all those DP states, the sum is now 1. Now, when I consider the coin 3, I from 0 transition to 3, from 2 transition to 5, from 4 transition to 7, and now from 3 I also transition to 6. This is also happens, just like 0 transitions to 2, 4, and so on automatically, because I have the for loop that iterates all the sums, and for each of them it transitions to the sum plus 2. When I consider the value 3, I again have a for loop that iterates all the sums, and for each it transitions to the sum plus 3, because no matter what sum you have, For example, maybe you have sum 11, and the way you create it is 2 plus 2 plus 4, this plus 2 plus 3. Let's say this. This is how you can get 11. Afterwards, you can use another 3. You can also use another plus 3 if you only used 2's so far. But though with 11 it's impossible. So no matter what we used before, we know that those were coins only 2 and 3 because only those we used. And for each here element, we transition by plus 3. And the dp for every index, it stores for this sum of values, what is the number of ways to get here. And then we transition using the next coin, which is 5. So from 0 we transition to 5, from 2 we transition to 7, and so on. That's the visual interpretation. If you don't fully understand this code, but you want to be better at dp, what is a good idea when learning and practicing is, for example, for this task, you want to, even after writing the code if you want, take this input and simulate everything that dp does on with pen and paper. So, you know, on paper you can draw, let's say, a table with the dp values. 0, 1, this is the sum, 2, 3, and so on. Initially, this is how we start. And simulate fully the dp. Then think after every coin, what is right now stored in this array, and it should be equal to number of ways to use coins so far to achieve every sum. Yes, I'm exploring all possible sums, and I do it only in increasing order of coins. Actually, in the order of coins that is given to me in the input. Note that here I didn't sort the coins, because even if they were given in random order, like 2, 5, 3, that's still okay. I will then do it in order 2 plus 5 plus 3, that's fine. As long as you don't randomly shuffle the coins between of the dp transitions. Okay, I think we are done with this task. And it's not an easy task, this one. I think many people struggle with something like that. Removing digits. At Coder DP contest, you can post the link. I did that on, again, Aristo at Coder DP. Again, it's from 6 years ago, so I'm not particularly proud of the quality, but here's that thing. Maybe after next 5 years I will redo it. Okay. Removing digits. You're given n. On each step, you may subtract one of the digits from the number. How many steps are required to make the number equal to 0? I recall that there is a greedy solution that works here, and for some reason it is actually optimal to always subtract the biggest digit. I think it's hard to prove, and I'm not going to code it that way. I'm going to code it using dp because I know that it should work. We minimize number of steps. So dp of something will be minimum number of steps, well, to get here. We start at n, so dp of n is 0, just like in 3 problems ago. Everything else we need to mark as infinity, like in BFS or Dijkstra, to say those are impossible. I want you in the future to minimize it with something else. You might not like the fact that I always call the dp array dp. Actually, more meaningful would be minimum number of steps. But sorry, I'm just used to calling it dp. And if I want to write down the definition, I write it down, and it often helps to exactly specify what it is. So dp of, let's say, value x is minimum number of steps to get number x, with number of operations. For every x value from n up to 1, because from 1 we still need to transition, from 0 we don't transition anymore. we here subtract one of the digits. I could theoretically do it this way for every digit. Well, 0 is not really a digit that I can transition with. For every digit, if x contains digit, then consider the transition. But this is not very efficient. Again and again, I would need to check if x contains digit, and it increases the time complexity. Like it's roughly 10 times 10, let's say. Instead, what I will do here is iterate digits of x directly. For every character in the string version of x, the digit is that character subtract 0 character, so now it's actually a value from 0 to 9. If this digit is from 1 to 9, actually I think it wouldn't be incorrect to do transition with 0, but it would be strange. So if this digit is, let's say, just not 0, though maybe unnecessary if, I think. If this, then we do a transition from x to x minus this digit. We minimize in this task, so I say dp of x minus digit is minimum of itself, and dp of x plus 1 operation. You might think that this is incorrect when number x has some digit multiple times. If I have 551, then should I transition by 5 and by 5 again? Well, when we minimize, it doesn't hurt. If you multiple times apply the same minimum, it doesn't matter. If this was a counting problem, if we needed to count number of ways, we would need to here get rid of repetitions. But I don't need to. At the end, output dp of 0. Zero, that's not good. I need to fill with infinity. Very often when you see 0, it means that in minimizing problem, it means you set everything to 0, so nothing happens, because minimum of 0 and something else is 0. Isn't the time complexity the same? No, it's not. Now the time complexity is n multiplied by the length once, because in this for loop what happens, we cast number into a string, which takes, let's say, 10 operations if the string is of length up to 10, or here 6. And iterating it doesn't increase time complexity. You iterate each of those 6 elements which are stored in memory. This is not length squared, this is length, and that's it. So the time complexity is of x times length. Formally, the length is log of x, the decimal logarithm of x, but the constants you can skip, so it's log of x. This is, by the way, kind of problem where only, or maybe push dp is the main way to do it, because you iterate what you can subtract from here. So you have the current value x, and from there it's easy for you to propagate, to know what you can subtract now. Versus in pull dp, you would need to consider from what value I'm moving, and for each of those separately you would need to check if such a digit exists there. So here push dp is very convenient, versus that other method that so far today I did not show, the pull dp, is not very convenient. Maybe I will increase the font slightly because I have a lot of space, and the okay, 18 I think is enough, and the codes are short. Can we also do a BFS? Yes, we can. In this task a moment ago, we can do BFS. You can think about it as a graph with values from 1 to a million, but BFS will be slower than a for loop. Unnecessarily storing things in a queue is not necessary if you know that it's correct and valid to iterate them in order. But yes, VFS would be correct and it would have the same time complexity. Okay, next task, grid paths 1. Consider a quadratic grid with some squares have traps. It is not allowed to move to a square with a trap. Your task is to calculate the number of paths from upper left square to the lower right square. You can only move right or down. So here we start there in this corner, we want to get here. We count the number of ways. This time we don't have a sequence, so we likely want to have dp state for every cell. Hence, most likely dp of row column is equal number of ways to get here. We start from the top left corner, and at the end we output the value for the opposite corner, n by n. That's likely what I want. We want to know the dp value for everything. Well, first let's read the input. Create two-dimensional array. I always use vectors because it's nice, modern, and you can fill some default values. If you use arrays, it's fine. You have this. I wonder if there can be a trap in our initial cell. Well, they say it's not allowed to move to a square with a trap, but can I start there? Not sure. I will say if grid of 0, 0 is a trap, then output 0 immediately. Or you can change this to 0 and then everything will be 0. I'm not sure if needed, if this is needed. Not sure if needed. If it can appear in the input even. I will not today answer questions unrelated to what I'm doing. I want to do it educational stream on problem solving DP problems. And because there are more than 20 problems, I want to do them in 2 or 3 streams. I will not show multiple methods. So if I think that the push method is the best to solve something, this is what I'm doing. And in particular, I also don't show recursive methods today, unless I think that this is the easiest way to solve. There are just too many problems to solve. Maybe another day I will make a separate lecture where I take one problem and I solve it in 3 ways, 3 different ways. Now, as always, we iterate. Note that even though we have a 2-dimensional problem, the description of what I'm doing here is iterate all the states. Earlier it was indices or the sum. Now it's the cells in a grid. I have dp of row column. Actually, I will use, I think, pull here, because I will first use push, and I will show you how simplified it gets if we use pull. I have this already. This is the number of ways to get here. I now can move to the right and I can move down. So maybe two transitions, move right. If column plus 1 is in the grid and grid of row column plus 1 is empty, it's allowed to go there, then we transition to this neighbor. So if we had 5 ways to get here, all those ways can be extended and we can get there. There are now 5 new ways to get there in that right neighbor of mine. Also move down. Why is it 4? It's an if. If row plus 1 still fits, add self. This is the modulo function that just adds 2 numbers and applies modulo fast with an if instead of modulo operator. Move down. And I think this is correct, and I'm going to submit it. The time complexity is obvious, n times n. Same is memory complexity, even though actually memory here can be optimized because you can move row by row, but nobody solves such a problem this way. accepted. Now I will replace this with pull. So the visual representation of push dp is that you are in some state, for example here in a cell, and you know its value, dp is equal 7. There are maybe 7 ways to get here from the start. 4, 5, 6, 7. 7 ways. And now you propagate this value further. For each of your 2 neighbors, you say your dp value increased by 7. This is the push dp. For every cell, you know the value here, you propagate 2 neighbors. Versus, let's maybe decrease this. The pull dp works like this. You iterate the state or the cell, and you want to compute this dp value. dp is equal to question mark. You don't know it yet, you want to compute. This will be pull. You take it from the 2 cells from which you came here. You don't iterate the next move, you iterate the most recent move. What is the previous move before I get here? So what you say is that the sum of those 2 cells, let's say this is A, this is B, I put here. So this is A plus B. And that's simpler code because it can be done in one line with some out of bounds possible errors, but we'll see how it goes. So everywhere here, except for the starting cell. The starting cell I cannot move. So if row is 0, what's happening? Okay. If row is, now pull method. If this is the starting cell, then for that I already initialized the value. So continue. But for everything else, dp of row column is simply the sum of 2 previous neighbors with modulo applied. Push method below. You have this, where column -1 and row -1 might be out of bounds. There are 2 ways to fix that. One is to make a bigger dp array and to pretend that the grid is surrounded with extra walls. Or another is ternary operator. If row, then this, otherwise you use a 0. If column, then this, otherwise use a 0. That's just an implementation trick to avoid ifs and to avoid, well, to avoid runtime error here, because you don't want to allow this to be taken if row is equal to 0. At the end we output that, and you might notice that right now I'm not checking if some grid contains a trap. So I will say that only if grid of row column is equal to a dot, then I'm doing this. Let's see if that works. Oh, I didn't even run for the input. Free. Okay, now I think it works. Same time complexity, shorter code. Arguably because of that, pull method is here better. So this is pull method. You iterate state, and dp of that state you set equal to the sum of all possible previous moves, or the dp values from possible states, possible previous states. You're doing dp. Okay, cool, Dragon. Indeed, I have some content in Polish. No, I'm not doing PhD. Yes, we can avoid modulo operator here. I'm too lazy, I will not do it. Bookshop. Modulo, no. Here's the new problem. Here's the new problem. Everything works good. Again, quick add. 10 days ago I announced on Codeforce's big group classes where we solve all Codeforce's problems that I choose, that I think are educational or just nice. There are two groups. One is for roughly Division 2 and one is roughly for Division 1. You can look up the details in Codeforces. I'm pasting a link. I hope that more people will join in the next few days. We'll see. Bookshop. You're in a bookshop with which sells different books. You know the price and number of pages of each book. You have decided that the total price should be at most X. Now it's different than previously because so far always we aimed at exactly X. Now it's at most X. What is the maximum number of pages you can buy? You can buy each book at most once. Well, this problem has a name. It's called knapsack, where you have n items each with some price and some reward. And given the total budget that you have, or the total size of a knapsack, you want to maximize the total reward. There are the constraints here. In AddCoder DP contest, there are two versions of this task. It's called Knapsack 1, the standard version, and Knapsack 2, the modified version. Okay, now we have some items. So for example, item 1, 4 and 8, sorry, 4, price is 4, the reward or number of pages is 5. Item 2, price is, I'm rewriting from the sample input here. Item 2 has price 8, reward or the number of pages 12. Item 3 is something, and so on. This time it's a little bit similar to coins, and just like in one of the coins problem before, I needed to guarantee that the sequence is increasing. Here I need to guarantee that every item I buy only once at most. So I cannot do dp of sum. So dp of, let's say, total price is maximum total reward so far. It's invalid to only do this dp and then iterate always every coin or every item, and I consider adding it, because possibly you will consider that you will take first item 1, then item 3, then item 1 again, item 2, item 1 again, item 3, and so on. This is not allowed. Because of that, we need to iterate items in order. So for sure, it's hard to avoid it unless you do extra dimensions in your array. Almost for sure, your first for loop will be to iterate the items here. Or a book. I will say item. And only here inside you will iterate the sum. And the sum, the dimension that you have a condition on, is the total price. Maybe sum is here confusing because we have the sum of two values, so I will actually here say total price, or maybe S price, sum of prices from 0 up to X. Very similar to one of the coin problems. Let's maybe read the input. There is price of every book and the number of pages. I will rename it as reward. The pages are confusing, like why are we maximizing that? Normally it's weight of an item and value, monetary value that we maximize. Okay, input done. And now the DP. There will be DP, maybe long is needed. 1000 elements, the value is up to 1000. No, so I think long is not needed. So there is this. The total price goes up to X, so we have this. Maximum number of pages you can buy. DP of some price is max total reward with this sum of prices. That's the definition. And I can say, theoretically, I should say this. For the sum of prices 0, the total reward is 0. And everything else I can set to negative infinity. But actually, I don't care that the DP thinks that the sum of prices 5. If I spend $5, I also can get a reward of 0. That doesn't hurt, it's just not optimal. So actually, I don't need to do anything. This is not necessary. Unnecessary. By default, everything is 0, and it means that every total price that I spend, the sum of prices for each of them, the max total reward is 0. So I spend $7 and I get nothing for it. I don't need to do anything else with it. That being said, it would also be correct to fill it with negative infinity. If you maximize, then start from negative and do that. This is correct code, but this is also correct code. And no, it doesn't work here to greedily take something with best reward to price ratio, because you might then just barely not have enough money to buy something else. So maybe you will buy one thing, and then the amount of money you have remaining, you cannot optimally spend all of it. Versus you can get things with similar ratio of reward to price and actually spend close to all your money. Because of that, the greedy solution that you suggested, Sakun, does not work. Okay, and now for every item I have this price, and I transition just like in the second coin combination. So the coin combinations 2, which was the fourth problem today, is very, very similar to that. You can treat that one as introduction to knapsack. I will transition from dp of s price to dp of s price plus the price of this item. This is the transition that I'm doing. So dp of s price plus price of item, minimum of itself, I'm just too lazy to type so far, of myself. So this is the total reward so far, plus the reward for this item. For example, maybe so far I spent $100. The total reward, dp, is equal to, let's say, 1,000. This is total reward. Now I see an item that costs $5 and it has reward equal to 17. From that, what I will transition to is that dp of, for $105 total, I can get a reward of 1,017. For such data, this is the transition I would do. That being said, it's not equality, it's minimize, because maybe this already was set to something, sorry, maximize, not minimize. Maybe it was already set to something greater, then I don't want to override the better possibility. Now, when you have a bigger DP task and it starts getting annoying to rewrite this, so I can do this, but I don't like it, it's longer line. Then I also have a helper line max self, or I usually call it maxi, not to repeat a long thing like this. So this thing maximize with the second thing. As always, I don't want to exceed the bounds. Let's see. Nothing printed. Now, dp of x theoretically should not be enough, because they are saying that I don't need the total price of exactly x. So it seems that what we need to say is the maximum in the full dp array. And this, it's clear that this should work. Also, it's clear what is the time complexity, because it's n times x, which barely is okay. It's 1,000 times 100,000, so 100 million. 16, oh, it's bad. price, reward. All right. In the coins problem, you can use every coin multiple times. Here, they say that the book should be considered at most once. The bad thing is that if I have something that costs, let's say, $4, and the reward is 10, what my DP will do is it will say, okay, I start with this thing, then DP of 4 is 10, I can spend the total of $4 for the reward of 10, but then I can also do this. I can spend the total of $8 with the cost of 20, and so on. If I make a for loop that iterates this sum so far, the sum of prices, from 0 up, then I consider multiple transitions like that. To fix that, I'm going to do this thing backwards, actually. This thing is incorrect. Allows buying same item multiple times. Because now what happens is, if you start with that, and this full array of 0 to x, you iterate backwards, when you get to 0, you transition to DP of 4 is equal to 10, but you will not still be at 4 to transition from there. If this is confusing to you, think what is the difference between such for loops. Consider a problem. You are given a sequence, compute prefix sums. To compute prefix sums, the code that you should do is something like this. A of I plus equal A of I minus 1. Because we do it in this order, the values propagate further and further. Every value gets propagated all the way to the end. So it gets reused multiple times, up to the end of the sequence. But if the task is, you're given a sequence, add every value to the next one, but without propagating further. If you have sequence 4, 6, 5, 10, 20, if you only want 4 to be added here, so you want to get here 10, 6 you want to be added here, so you have 11, 5 you want to be added here, so you have 15, 10 added here, so 30. If you only want to achieve this, then the correct way to code it is go backwards. Doing this, what happens is to 20 you add 10, it becomes 30, and then you continue with this remaining part without touching this. So when you go backwards and always index affects the next index over the next indices, this guarantees that the value from any position will only be used once, or in all the transitions that you consider from there, but it will not be propagated further. So in the same for loop, this thing is not reused multiple times. Or in our problem, the same state of the DP does not consider using the same book multiple times, and because of that transitioning, for example, from DP0 to 4, 8, 12, and so on, which would mean buying this book multiple times. So that's the prefix sums which apply the number all the way to the end, and when you go backwards, it applies only to what you tell it to do here. Again, that's not maybe very obvious, clear, and so on, and it's okay if you don't fully understand, and after the lecture you can spend more time analyzing that. But I think this is a good thing to analyze. Again, you can take some input test, maybe smaller than this, and simulate it with pen and paper without computer. You could also do pool, yes? Yes, that's correct. Yes, you can also do copy of the DP vector. Because so far I did not do it, I'm fine with this code. Again, too many problems to consider multiple solutions per problem. Maybe another day I will take a problem like knapsack and make a YouTube video with multiple solutions. Let's see if now it works. 13. Today I'm only answering questions about the lecture. Okay. Book shop. We have that much time. I think we will get to around here, maybe LCS as well, and then that will be it for today. I'm aiming for 2 hours today, and I think it seems reasonable to roughly do 10 problems one stream, maybe 7 problems second stream, around 7 problems last stream. We need to consider the fact that those problems closer to the end are harder and thus more time consuming. Do all the lectures coming to YouTube? So whatever you see me streaming on Twitch, it comes to YouTube, yes. And will I cover all the CSES problems? No, not all of them. One moment. Okay. Array description, modulo. Let me copy what I need. Follow-up lecture on DP. I will for now make a series of 3 streams with problem solving those DP tasks here. There is an array with n integers in this range. The absolute difference between 2 adjacent values is at most 1. Some values are unknown. Your task is to count the number of arrays that match the description. So there are question marks. For example, if there is a 2, then question mark, question mark, question mark, then a 3, question mark 5, and so on. You want to count the number of ways to replace question marks with numbers. 2 neighboring values can differ by at most 1. And some stuff here you can decide, let's say greedily, between 3 and 5, if there is something here and the neighboring values differ by at most 1, this needs to be 4. But here there are multiple possibilities. For example, you can do 3, 4, 5, 4, 3, or 3, 3, 2, 3, 3, and so on. Exponential number of options. As almost always in DP, we go from left to right, we go through the stuff that is presented to us, we make decisions or transitions, always after deciding stuff for already things we iterated, so for the prefix of the sequence, what is the relevant information that we need to keep to know what is the next step to move and when to stop and what answer to print. We need to maintain the number of ways because that's the answer. At the end we need to output it, but also to know what to replace the next question mark with, we need to know from that stuff, not all the question marks replaced, but what the most recent one was replaced with. So I need to know the value of the last question mark so far. And there is the current index. So I will maybe do this thing with 2-dimensional DP, just so we would practice it also with sequences. That being said, it's not necessary. I'm using it here though because I see that 100,000 times 100, it will easily fit in memory and in time, so I can afford this. Normally we had DP of I. Now 2 things are relevant because, well, if I just tell you, if I tell you that this is the input, and I say that the last value used, so the question mark most recently was replaced with a 4, and I tell you this input, you don't know what to do because you don't know where you are in the sequence. We also need to know the index. Now this, if I present to you those 2 values now you know what to do, you know what is possible next, and whether you should stop already and print the answer. Either this can be part of a for loop like in some of the previous problems, but this time I will put it as a dimension of dp. I will say dp of I and last value, number of ways to, let's say, to fill everything from 0 to I inclusive. It's good in the definition of dp to specify if it's inclusive or not. So for me it will be I inclusive, such that a of I is equal to last value. Maybe I will put here an x to be simpler. So the index I set that to x. Now it's not easy to initialize this dp because first number might vary. So I will need to do dp of 0 and something. Initially number of ways is 1. And then there will be transitions. Well, let's read the input. N, m. M is number, the limit for numbers. They are from 1 to m. I need to create array that goes n by m. And for now I will put here question marks. Sometimes it's hard to decide whether something should be n or n plus 1 and so on. In this problem I will show you how I usually do it in harder problems, which is I fill this at the end. I will leave it like that on purpose. Once I know what are the main for loops and transitions, I will adjust the size of the dp to that. Because at the beginning of coding dp problems, sometimes you might not know, and it's okay. Right, so what now? Let's focus on transitions. That's the most important thing. And everything else will follow. For every value from 1 to n, we will transition to I plus 1. So dp of I something transitions to dp of I plus 1 and here x plus minus 1, while deciding the value of ai plus 1. Because if this means that we already decided things up to I, that's my definition of dp. You can, by the way, define it differently. You can say that this means that you decided values up to I minus 1, and that's fine. The code will differ a little bit, but it's still correct. So you have this. So if you already decided I, and this is push dp, now you're deciding I plus 1. You're putting some value there. And what? And there are at most 3 possibilities for it. Well, I need to iterate the states, so also x. X goes from 1 to m. Let's say that the value, oh, and because I need to decide this, it doesn't make sense to do this transition for I equal to n minus 1. I will say that it goes only up to there, because when looking at position n minus 2, if everything up to that is decided, then you can still transition to n minus 1, which is the last element of the sequence, but when you are at n minus 1, you don't have anything else to do. And in particular, the answer, that will be the sum of dp of n minus 1 of everything. This is pseudocode right now. Because this means that everything from 0 to n minus 1 is decided. As always, look at the definition of dp if you have doubts about that. And I need to sum up everything. Note how I still have not figured out the exact size of the array. I will adjust it at the end, because this is the important stuff. And writing down what the answer will be, it helps me a little bit. But the order of solving such a dp task for me is to think about it, imagining some sequence, then defining the dp state, then doing the transitions. Often even I will not know exactly what are the for loops and whether this goes up to n or n minus 1, and I will start from doing the transition. I will start from doing this comment. Actually, this for me right now is the second most important line of the code, this transition, which is not even correct code. The most important is this, the definition of dp state. And in hard dp problems, very often 90% of the difficulty is deciding what this should be. coming up with the dimensions and so on. So coming up with what values are needed so I could make the next move, next transition. And then second most difficult step is to figure out the transitions. Are there lecture notes for today's lecture? No. But the codes that I'm presenting will be on my GitHub repository. Link will eventually be in the description of YouTube live stream recording. Okay, I can, if the previous value was x, then the new value can be among x minus 1, x and x plus 1. It needs to be still in the range. For now, let's say that it's a question mark and I can put whatever there. Then dp of I x transitions to dp of I plus 1 y. We do operations modulo, so dp of I plus 1 y plus equal dp of I x. Add self is the function that adds two numbers modulo, and it does them fast without the modulo operator. That's something that you want to generally use in competitive programming for the speed, when sometimes you're close to time limit otherwise. So we have this, but if something is a 0 in the input, that's a question mark, and I can replace that with anything. If this is a number that is non-zero, I cannot do anything else. So here, if, let's see, the x, no, not x, if the input of I plus 1 is not 0 and input of I plus 1 is not y either, then continue. Okay, that's the answer. Answer is 0 for all the values. Increase the answer by dp of n minus 1 x. I'll put the answer. And only now I will decide the range of the dp array here. I'm using indices I from 0 to n minus 1. So the size, the first dimension goes n. And the second, well, it goes up to m. So m plus 1 is the size of the array. Finally, we need to initialize. For the first element, either it's, so if input of 0 is equal to 0, then everything is allowed. dp of 0x is 1. And else dp of 0 and the input value is 1, if this is specified. There is a way to code this a little bit shorter way, where we actually transition from some fake element. You can pretend that before the first element in the sequence there is some fake element that is kind of a 0, a question mark, but I think it's more clear that this works, so I will leave it like that. Oops. Anything else? Input. Well, let's read the input. What is going on here? Well, I'm solving competitive programming problems. And the stream should be understandable, but sadly only to people who already are doing some competitive programming. It's not that much for beginners. Sorry. What if there is no possible answer? 0 ways. Yeah, what then? Then the answer will be 0. The transitions consider all the legal transitions. It is possible that they will sum up to 0. For example, if let's say the input is that there are two elements, m is 10, the first element is 3, the second is 7. Oops, typo. No question marks at all. If I run my program, 0. It's not an edge case. I consider from 3, I consider moving to 2, 3, 4. For each of them, if it's allowed to me to put it here, if it matches the input value or the input value is 0, I will do the transition. It's a little bit like asking if you compute, I don't know, the product of numbers in the input, what if the product is 0? Well, then the program will get that. We're pushing value only if possible. We always push a value, sometimes it is 0. Okay. I would agree with your description if I said if dp of ix is equal to 0, then do this. Pushing values is always correct because it's always correct to say the following. If at position I put a 3, it's always correct to put value 2 at next position. But what happens is that possibly the number of ways to put 3 at position I is 0. If so, those 0 ways I propagate here. I understand how it's semantics, but yeah, that's what happens. Time complexity, as almost always so far, is easy to compute, n times m. Same for memory. Memory can be improved, but I'm not doing it here. Don't understand any code. Yeah, then, well, sadly, then the stream is not for you, but that's fine. If you want to watch, I'm not the Twitch police. Counting towers. What's input of I plus 1, not y? This means the input sequence specified that sometimes the values need to be exactly equal to something. If in the input there is a value 2, then you cannot put here a 3. Yes, in that previous task you could change zeros to anything else. Counting towers. Modulo. Yes, add coder beginner contest soon. This is why this is also a reason why I wanted to limit the stream to 2 hours today. There is add coder beginner stream, I think, in 25 minutes. And it's also why today I'm streaming earlier than usual. Wait, active contests, upcoming contests, this thing. Contest begins in 24 minutes. If you want to participate, you should register. This is actually good for beginners too. So if you are barely familiar with competitive programming, then add coder beginner contests are very good for you. Okay, I think last or second last problem today. Build a tower, counting towers. Build a tower with width 2 and height n. You have unlimited supply of blocks with width and height being integers. For example, here are some possible solutions for n equals 6. This is actually a hard problem, I would say. It's for the first time it's a problem that somebody experienced with DP could possibly not solve because of big limits. I will on purpose draw this thing horizontally. Counting towers. You can think about it this way. I can draw possible lines and we need to use some of them. But they need to form rectangles. For example, I can use a rectangle here, maybe a rectangle there, maybe a rectangle here, maybe there, and so on. And maybe this is one big rectangle, and then 2 small ones. The basic DP solution, the simplest possible DP solution here is that we need to try to go from left to right Always when we have this situation, we can look at or we can imagine that we look at the leftmost cell that is empty and we decide what we do with this cell. In particular, we can put this, we can make a transition where we do this or that or this and so on. Additionally, if something is filled fully already like this, and the length of first and second rows, how they are filled, is the same, then instead of doing one of those transitions, we can also do this transition or this transition and so on, something of height 2, the bigger rectangle. So the basic DP here, the basic description of what happened so far, we don't care if this is one rectangle or something split into two. We want to know how many cells are taken and where the next step should be, when the next move should be. So it's enough for me, as we go from left to right, which is almost always how we do it, is DP of how the first row is filled and how the second row is filled. What did I do? Oh, I did some very bad shortcut. How did I do it? Okay, chat ideas. I clicked some keyboard shortcut that completely messed up my resolution and how the monitors are treated. I think that my 3 monitors merged into one. I don't even know what you might see in OBS right now. Look at the bar on the bottom. I don't have bar at the bottom. Control what to reset? It's called magnifier. Okay, I opened magnifier. Okay, done. Whew. Windows, how to close magnifier. I mean, maybe how to open. That was Windows ++. To close, Windows plus escape. Let's try. That doesn't work for me. Oh, because I'm in Linux. Wait. Yep. Okay. That was very scary. I actually thought that I will need to restart the stream, which would be very annoying. And the way I actually realized what happened is that I could move my mouse around and it moved me between my 3 monitors, and I could go to the bar at the bottom, like actually Zakisimo suggested, and I saw one more application open, something that I did not open before. That was the magnifier. I just right-clicked and closed, and that worked without new keyboard shortcut. Okay, what you can do is as we go from left to right, number of ways to fill first row 1 cells of first row and first row 2 cells of second row. Right, and it's tricky that this avoids overcounting, because I don't want to separately count the possibility of doing, let's say, shape 1, 2, 3, versus what if I separately count 1, 2, 3. Those are the same shapes, they should not be counted separately. But if always you take the leftmost cell and you fill that, in case of tie is the top one, so you prioritize, you say that first, always, no matter what, you will choose what rectangle should be with this cell inside the top left corner. After you do it, you take this cell as the next available and you decide its fate. then here the leftmost cell available is this, and you decide its fate, to what rectangle it belongs, then every possible drawing will be counted only once. And with this, there are also transitions, so this is already O of n squared states. And for each, when you look at this cell, you have linear number of transitions, so times n transitions, the total time complexity n cubic. So very slow for such big n. Now, with such constraints, this would be a normal DP problem, already harder than previous ones from today. Here, what should we do instead? I believe that there is some formula or some kind of trick for that. I believe that the only thing we can afford, and even that we cannot afford fully, is to think that always a drawing splits into some parts. It splits into some parts that we do independently. For example, here we have this split here, and there should be a formula for the number of ways how we deal with this thing in between. Oh no, I have a better idea. I think there is a way to do it with such a formula, but I will do something else. I want to do transitions one by one, and let's maybe get back here. I will think about it more like drawing a drawing cell by cell or column by column. When I look at this column, instead of deciding that this cell belongs to this rectangle, if I was to iterate all those rectangles, there would be a linear number of them. I will only here decide that this rectangle starts here. This will be one transition instead of linear number of them. Can we consider the last few states recursively? That's too vague of a question. I don't know how to answer, Krish. So we decide maybe that this is what we do here, and there maybe we decide that this will be just a square one by one. The state, as we transition forward, the only thing that is relevant is that here we continue with a rectangle, and here we stopped and we have a border. So my DP state will only be one of few possibilities of what happened with the previous column as I move to the next column. I assume that the width is n, the height is 2. So if I was a moment ago in column, let's say I, then possibilities are that either I finished all the rectangles fully and this is fully drawn vertical segment, or maybe this is a drawn vertical segment and this is empty because I'm here, I need to continue a rectangle that is of height 1, or the other way around, like this. And finally, it's possible that both are empty, but there are two possibilities of how this happens. Either there is a rectangle here that I'm continuing, and there is a rectangle here that I'm continuing, or maybe there is a big rectangle that looks like that, that is continuing. I think in total I mentioned here 5 possible states of what happened in this previous, let's say, column. So I will aim at something like that. 5 here is 5 possible states of the description of what happens between columns I and I plus 1, where it's fully separated, or separated at the top, separated at the bottom, and fully empty, but either then both rectangles, both small rectangles are continuing, or one big one. Now, I think that this is not the intended solution. Before I code this, but I will code it, that's my solution. I will look up this. I recall that instead what we should do is something with the power of 2. where if we analyze what is the number of ways to do a few consecutive rows, then 2 at power n is involved. I solved this problem before, so I should know. It's just that right now I don't remember. Oh, they do it with my method, but just this. Oh, this is my solution, but simpler, so I think it's better if I describe that. I believe, but again, anybody remembers in the chat the solution with formulas? Is it okay to ask questions about programming? I will not answer today because I'm doing something else, sorry. I sometimes have streams where I talk more with the chat. This is not such a stream. Okay, so another thing is, maybe it's only needed for this previous column. So for this previous column, it's only needed if we continue with 2 separate rectangles there, like this, or there is nothing here. This is one big rectangle. And when I transition to the next column or row, I will decide if it's still like this or if it doesn't have that. So think about it this way. We are making this drawing. We are painting this drawing column by column. I will only have this. dp of I 0, number of ways to paint everything, paint segments, so choose exactly how the drawing will look like, up to column I inclusive, such that the short horizontal segment is no, yes, drawn. Let's say this. That's my definition, where this is 0 or 1. By short horizontal segment, I mean this part, because depending on this, whether this is drawn or not, it describes if we have 2 separate rectangles or one big one. It's a little bit like merging neighboring cells, I guess. And when, for example, this is drawn, then what happens next is that it can be drawn again, and you have a choice of cutting this here and cutting this here, in total 4 possibilities. So don't cut, so extend both, or extend one, or extend the other, or extend neither, or both. So 4 ways. Versus if you have, for example, this thing here and you want to here start something new, you need to draw those segments. If I tell you that here nothing is drawn, here it is drawn, this means that 2 new smaller rectangles start. So there is one way, and so on. We need to figure out for transitions. And there are test cases. But I'm guessing we will do just one DP that goes up to 1 million. And then for every test case, I will answer in constant time. Let's use an array. When you have 2-dimensional vector, it's not good if the last dimension is small, because small vectors have big overheads. It takes way more time and memory. Okay, definition. dp of I 0 or 1. This is number of ways to paint. Decide the state of segments up to row or column I, such that this small, the middle segment in column I is drawn or not drawn. That's the definition. I start, I think, by saying this, because for the first row there is a way to put here the small segment or not put it, so to put one big rectangle. Let's here make this array by 1 bigger. We now transition, and there are 4 transitions. dp of, well, add self. dp of I plus 1, 0, something times dp of I 0. Depending on whether this middle segment exists in one row versus next, I need to figure out the number of ways to transition in between. For example, I already said that if this middle segment exists both here and there, so if I know that here I have 2 separate rectangles, here I have 2 separate rectangles, then in between I can put segments separating them, but I don't need to. So there are 4 ways. And with 4 I need to do it as a long and apply modulo. Otherwise 4 times value up to 1 billion would overflow. If there is nothing here, if this is part of a drawing, then I need to separate here. This is not a valid drawing. I cannot have here that there is some big rectangle, but it doesn't stop here and I start new separate rectangles like that. This is not valid. I then need to have stuff here and there is one way. So this is 1, this is 1. And finally from 0 to 0, I think that will be a 2, because if you know that there is big rectangle that possibly ends here, and this is empty, there is nothing here, and this is a big rectangle, then you have a way of continuing here without a separator, or you can put a separator. So this is valid, but also this is valid where there is nothing here in between. 2 ways. I'm also applying modulo here, otherwise this function does not work. There are slightly faster ways to apply those operations, whatever. Then for all the test cases, I'm guessing that the answer is the sum of both, but I will think in a moment. Let's see. No, n-1, because index 0, it meant column 0. When you considered the n-1, then this row or column n-1 finishes the rectangle of size n. And in this last one, you can have this middle separator, or you cannot have them. Both options are allowed. So I think we're good. Yes, it works. The time complexity is O of n plus every test case you solve in constant time. So let's call this O of t plus n. Maybe t plus max n. Submit. I would argue that this is 10 times harder than any previous problem. Maybe coin combinations 2 is also confusing, but this one is just a hard problem to solve. And I would imagine a scenario that even I, with years of experience, I could during a contest be stuck on this for some time without coming up with a solution, going into an incorrect idea. Yeah, matrix expo can be used here when you have, because here you have only 2 states, you have transitions where you just add with some multipliers to next. So indeed, Having, there is matrix expo solution. This is matrix multiplication. You multiply vector by matrix. Also, you can solve this in, if not for test cases, you could solve this in constant memory. What is your approach to such problems? What do you mean? I've just showed you all how I approach it. You saw me live thinking about it, and I actually didn't remember the intended solution. I thought that we will use some formula like 2 at power something, at least to consider segments. in my mind I had some kind of prefix sums in mind, so I wanted to go in completely different direction. I then came up that we can, to speed up the transitions, we can just few of them if we go row to row, not we just remember the full shape so far. And then when I googled, I saw actually two states instead of 5 are possible, so I overcomplicated. That was my approach. I'm not sure how else you could describe this or what hints I could give you. Okay, 2 minutes to add coder task, to add coder contest, so I think we're finishing now. I think we did 9 problems out of 23. Good enough. The next stream will be tomorrow. Not sure about the date, the time exactly. This is the blog describing my group classes. Please join if you're interested. What percent of problems I solved on my own with help? 80%. How much math is required in CP? I have no idea how to measure that, John Wick. Good luck in the AdCoder contest to everybody who participates. The AdCoder beginner contest is here, contests upcoming. So if you want to participate, it starts in 1 minute. See you again tomorrow. Not sure if same time. I will announce on Codeforces. There will be countdown. So see you all tomorrow for the next 8 problems or so. Maybe again in 2 hours. Then on Monday or Tuesday we will finish the remaining problems. Yeah, thank you, Krish, for commentating and for questions. Have a good day, everybody.